Right, so we're looking at empirical formula and molecular formula. And this is a bit of a recap from this side, because we did look at empirical and molecular formulae then. But the questions get a fair bit harder in chemistry. They're much less obvious that that's the way to answer that kind of question. For example, the last question on the assignment is an empirical formula question, and most students find that one quite challenging. So the empirical formula is the smallest whole number ratio of elements in a compound, whereas the molecular formula accounts for all of the atoms present in a molecule. And so, for example, in our booklets we've got hydrogen peroxide that has a molecular formula H2O2. If we look at the actual ratio, then that would be 2 to 2. And if we simplify that to the simplest ratio for the empirical formula, we get 1-to-1 ratio, which then means that the empirical formula is HO. If we look at another example of glucose, C6H12O6, we consider the actual ratio. We've got 6 carbons to 12 hydrogens to 6 oxygens, which means that the simplest ratio in the empirical formula, the simplest ratio is going to be 1 to 2 to 1. So our empirical formula would be CH2O. Does that make sense? Right, that's good. Some things, for example, the example here is of the sulfuric acid. If I look at the actual ratio for this, it's 2 to 1 to 4. Well, there's no way of simplifying that. So my empirical formula is going to be the same, because I can't simplify it, obviously, with that one there. Most people, I think, can do this part quite well. Determining the empirical formula when given the molecular formula seems okay. Problems come in, sometimes are going the other way. Like, so if you've got the molar mass of the substance and the empirical formula, trying to work out the molecular formula is the problem. So let's have a look at the example on page 31. Right. We're told that an oxide of chlorine contains 18.4% oxygen. So we've got chlorine and oxygen present. If I've got 18.4% of oxygen, then what I have of chlorine is going to be 100 subtract 18.4. We always then divide by the atomic mass. For elements. And hopefully the reason why you divide by the atomic mass makes sense if you think that what we're trying to find is the number of moles. And we know that n is equal to the sample mass divided by the molar mass. Well, in the case of an element, the molar mass is the atomic mass. Okay, so in this case, N is equal to the sample mass, percent, divided by the atomic mass of that element. And then we end up with this mole ratio. Okay, this is a mole ratio. But it's not that helpful in its current format. We want to get it now into whole numbers. And the way we find it in as whole numbers is we divide everything by the smallest value. Which then, obviously, the one that gets divided by itself is now converted to 1. And the other one is going to be approximately equal to 2. Yeah, 2.299 divided by 1.15 is going to give us approximately 2. So therefore, the empirical formula Cl2O. Doesn't matter which order. If you wrote OCl2, that's either way, it doesn't matter. Okay. When you're asked to find the empirical formula, don't stress about the order. So this was part A. And a lot of people can do that sort of thing, but we struggle when we get to part B. We're told the molecular mass is of our unknown is 87.0 grams per mole. And we want to find out what the substance is, so that's what we're after. We know the empirical formula, so we need to find the empirical mass. It's going to be 2 lots of chlorine plus 1 lot of oxygen. 87.0 grams per mole, approximately. So, the empirical mass is equal to the molar mass. Therefore, the empirical formula is equal to the molecular formula. So it's not really that useful an example because they were the same. But if they weren't, what we do, in fact what I'll do is I'll show you the working step. We're going to divide the molecular formula by the empirical formula. And that is why, therefore, the molecular formula is Cl2O. The empirical one is always on the bottom. Okay, that it can either be the same or less than the molecular formula. It can never be more. So it's going to have the same mass for the situations like we had with the sulfuric acid, where they're the same. Okay, so if the molecular formula and the empirical formula is the same, it's obviously going to have the same mass. But for every other kind of relationship where the empirical formula is simpler, is a smaller number than for the molecular formula, then the empirical formula mass would be less. Yeah? And as it says there, the exam has thrown up some real doozies in the past. This is true, and I think there might have been one on last year's exam which I might give to you as a little fun test to do.